Ask someone to name the strangest planet in the solar system. They will say Jupiter, maybe Saturn, possibly Venus. Almost nobody says Mercury. It is the smallest planet, the closest to the Sun, a cratered rock that most people assume has nothing interesting to offer. That assumption is wrong. Mercury is roughly 70% iron core by mass. Its magnetic field is offset from the planet's center by 500 kilometers in a direction no model predicted. Its surface is covered in bizarre depressions that exist nowhere else in the solar system. It holds water ice at its poles, despite surface temperatures hot enough to melt lead. And the leading explanations for how it became this way contradict each other. The planet people think about least may be the most structurally bizarre world orbiting our star. If you enjoy the kind of science that makes you rethink what you thought you already knew, do us a favor and hit like and subscribe. We cover the stories the universe is quietly telling, the ones most people walk right past. Are you comfortable? Now, let's begin. There is a planet in our solar system that almost everyone has forgotten. Not forgotten in the literal sense. People know it exists. They remember its name from school. They can usually place it in the lineup if asked. But when the conversation turns to the wonders of the solar system, when someone asks which planet fascinates them most, Mercury almost never comes up. Jupiter gets the attention, Saturn gets the rings, Mars gets the rovers and the dreams of colonization. Venus gets the greenhouse horror story. Even the ice giants out in the dark, Uranus and Neptune, get more curiosity than Mercury does. And the reason is simple. Mercury looks boring. It is the smallest planet in the solar system. It is the closest to the Sun. When people picture it, they picture a grey, cratered, sun-scorched rock sitting too close to the fire to be interesting. A dead world baking in silence. End of story. Except it is not the end of the story. It is not even close. Mercury is one of the most scientifically unusual objects in the entire solar system. Its internal structure does not match its size. Its surface chemistry does not match its location. Its magnetic field does not match any straightforward model of how small rocky planets should behave. And the explanations for why it became this way have been fighting each other for decades without resolution. The planet that seems like it should be the simplest one to explain turns out to be one of the hardest. But before we get to what makes Mercury strange, we need to understand why it seemed so ordinary for so long. Because the story of Mercury is partly a story about assumptions, about how the most overlooked object in a system can quietly be the most revealing one. Start with the basics. Mercury orbits the Sun at an average distance of roughly 58 million kilometers. That is less than 40% of the distance between Earth and the Sun. At that range, the Sun dominates everything. It fills the sky. From Mercury's surface, the Sun would appear roughly 2.5 times larger in diameter than it does from Earth, and at closest approach, more than 3 times larger. The intensity of solar radiation at Mercury's average distance is roughly 7 times what Earth receives, and at perihelion, when the planet swings closest to the Sun, it spikes to nearly 11 times. The dayside surface temperature can exceed 430 degrees Celsius. That is hot enough to melt zinc, hot enough to melt lead. Hot enough that for a long time, scientists assumed anything volatile, anything that could evaporate or boil off under extreme heat, would have been driven away from Mercury billions of years ago. Then comes the night. Mercury rotates slowly, but not in the way most people assume. For a long time, astronomers believed Mercury was tidally locked to the Sun, the same way our moon is locked to Earth, always showing one face to the star and keeping the other in permanent darkness. That would have been the simple, expected outcome for a planet this close to the Sun. Tidal forces should have grabbed Mercury and slowed its rotation until one hemisphere was permanently scorched and the other was frozen in eternal night. In 1965, radar observations from the Arecibo radio telescope in Puerto Rico shattered that assumption. Mercury is not tidally locked. It rotates, but it does so in one of the strangest rhythms in the solar system. Mercury completes exactly 3 rotations on its axis for every 2 orbits around the Sun. This is called a 3-to-2 spin-orbit resonance. No other planet does this. It means that a single solar day on Mercury, measured from one sunrise to the next, lasts roughly 176 Earth days. 2 full Mercury years pass in the time it takes the Sun to go from noon to noon. The geometry of this resonance means that certain longitudes on Mercury receive direct sunlight at perihelion, when the planet is closest to the Sun and solar intensity is highest, while other longitudes receive their noon sun at aphelion, when the planet is farther away. The result is that specific regions of the surface get systematically more heat than others, an asymmetry that has consequences for surface chemistry and the behavior of volatile materials that scientists are still working out. On the night side, temperatures plunge to roughly negative 180 degrees Celsius. The temperature swing between noon and midnight on Mercury is over 600 degrees. No other planet in the solar system experiences anything close to that range. The lack of any meaningful atmosphere means there is nothing to circulate heat, nothing to buffer the transition. Mercury has an exosphere, a vanishingly thin scattering of atoms kicked off the surface by solar radiation and micrometeoroids, but it has no atmospheric pressure worth measuring. The boundary between blazing light and frozen dark is sharp and absolute. All of this reinforced the same picture. Mercury was an extreme environment, yes, but a simple one. Hot on one side, cold on the other, no real air, no liquid water, a battered surface that looked indistinguishable from the moon when viewed from a distance. There was nothing there that seemed to require a complicated explanation. And then there was the size. Mercury's diameter is roughly 4,880 kilometers. That makes it smaller than Jupiter's moon Ganymede, smaller than Saturn's moon Titan. Both of those moons exceed Mercury in physical width. A planet smaller than 2 moons does not, on first impression, inspire the expectation of complexity. Small things in the solar system tend to be geologically dead. They cool quickly. Their interiors solidify. Their surfaces freeze into whatever configuration they last held and stay that way for billions of years. The moon is the most familiar example. It is roughly the same visual archetype that people apply to Mercury, and for most of the 20th century, that comparison seemed entirely appropriate. Here is where the first crack appears in the simple picture. Mercury's mass does not match its size, not even close. Despite being only slightly larger than the moon in diameter, Mercury is vastly heavier. The moon has a mass of roughly 73.5 billion trillion kilograms. Mercury has a mass of roughly 330 billion trillion kilograms. That is nearly 4.5 times the moon's mass packed into a body, only about 40% wider. If you had 2 spheres sitting on a table, and one of them was that much heavier than the other, despite being only modestly larger, you would immediately know something was different about what was inside it. What is inside Mercury is iron, a staggering amount of iron. The measurement that first signaled something unusual was Mercury's density. Density is mass divided by volume. It tells you how tightly packed the material inside an object is. Water has a density of 1 gram per cubic centimeter. Rock, depending on the type, ranges from roughly 2.5 to 3.5. Iron sits at about 7.8. Earth's average density is 5.5 grams per cubic centimeter. which reflects a mix of rock in the mantle and crust and a dense iron-nickel core at the center. Mercury's average density is 5.43 grams per cubic centimeter. At first glance, that looks similar to Earth's, almost the same number. But that similarity hides an enormous difference. Earth is a much larger planet. Its interior is under far greater pressure because there is so much more mass pressing inward. That pressure compresses the material at the center, squeezing it into a smaller volume and artificially inflating the density measurement. When scientists correct for this effect, when they calculate what each planet's density would be if you could somehow remove the compression caused by gravity, the picture changes dramatically. Earth's uncompressed density drops to roughly 4.4 grams per cubic centimeter. Mercury's uncompressed density is roughly 5.3. Mercury, the smallest planet in the solar system, is denser than Earth when you remove the effect of size. That number is not a curiosity. It is a statement about what Mercury is made of at a fundamental level. The only way to produce that kind of uncompressed density is to fill the planet with metal, specifically iron. And not just some iron at the center like every other rocky planet. Mercury requires an iron core that is grotesquely oversized relative to the rest of the body. The numbers are striking. Mercury's core extends to roughly 85% of the planet's radius. The core accounts for approximately 70% of Mercury's total mass. To put that in proportion, imagine a peach. The pit at the center of a peach takes up a modest fraction of the fruit's volume. The flesh surrounds it thickly. Now imagine a peach where the pit fills almost the entire interior and the flesh is just a thin skin barely coating the outside. That is Mercury. A massive iron heart with a whisper of rock wrapped around it. The sheer physical scale of this drives the point home. Mercury's iron core has a radius of roughly 2,040 kilometers. The rocky shell surrounding it, everything that is not core, mantle, and crust combined, is only about 400 kilometers thick. On Earth, the mantle alone is nearly 2,900 kilometers deep. Mercury's entire rocky envelope, the part of the planet that on any other world would contain the bulk of the geology, the volcanism, the tectonic history, is compressed into a layer thinner than some features on Earth's own surface. Compare this to the other rocky planets. Earth's core extends to roughly 55% of its radius and accounts for about 32% of its mass. Venus is similar. Mars has a core that is roughly half its radius and maybe a quarter of its mass. Mercury is in a different category entirely. It does not just have a large core, it has a core that dominates the planet so thoroughly that the rocky mantle is almost an afterthought. If you removed Mercury's silicate shell and looked at what was left, you would see a bare metal sphere nearly as large as the planet itself. Mercury is not a rock with iron in the middle. It is an iron ball with a thin coat of rock. This is the first and most fundamental reason Mercury is strange. Its internal proportions are wrong. Not wrong in the sense that they violate physics. They do not. Iron is a perfectly normal material for a planetary core, but the ratio is wildly different from every other rocky planet we know of. Something happened during Mercury's formation or early history that either gave it far more iron than expected or removed far more rock than expected. Either way, the result is a planet that looks like a leftover core, a planetary interior that somehow ended up with almost no exterior. For most of the 20th century, this was considered an interesting oddity, but not a front-page scientific mystery. The leading explanation was straightforward enough. Early in the solar system's history, the inner planets were still forming through violent collisions between rocky bodies. Mercury, the thinking went, had been a larger planet at some point, perhaps closer to Earth in size and composition. Then, a catastrophic collision with another large body stripped away most of its silicate mantle, leaving behind the dense iron core with only a thin veneer of rock. It was a dramatic story, but it was neat. It explained the density, it explained the core fraction, and it required only one event, one giant impact, to account for Mercury's weirdness. For decades, that explanation held. It was not proven, but it was plausible, and it had the advantage of being the simplest story that fit the available data. The problem was that the available data was almost nothing. Mercury is extraordinarily difficult to observe from Earth. It never strays far from the sun in the sky, which means it is always seen low on the horizon, either just after sunset or just before sunrise. Peering through the thickest and most turbulent part of Earth's atmosphere, telescopic observations are blurred and limited. Ground-based astronomers have spent centuries squinting at Mercury through the atmospheric murk and learning almost nothing about its surface. The planet, that is nominally one of our closest neighbors in space, has historically been one of the most poorly mapped objects in the solar system. There is an old and probably apocryphal story that Nicolaus Copernicus, the astronomer who placed the sun at the center of the solar system, never once saw Mercury with his own eyes because of the fog and low horizons of northern Poland. Whether or not the story is literally true, it captures something real. Mercury hides. And yet Mercury has played one of the most important roles in the history of physics. Its orbit is not a perfect ellipse, it precesses. The point at which Mercury makes its closest approach to the Sun shifts slowly around the Sun over time, tracing out a rosette pattern. Most of this precession is explained by the gravitational pull of the other planets, mainly Jupiter and Venus. But, in the 19th century, the French astronomer Urbain Le Verrier calculated that after subtracting all known gravitational influences, there was a small leftover precession of roughly 43 arcseconds per century that Newtonian gravity could not account for. This tiny discrepancy haunted physics for decades. Some astronomers proposed a hidden planet called Vulcan, orbiting closer to the Sun than Mercury, tugging its orbit forward. No such planet was ever found. The mystery was not solved until 1915, when Albert Einstein published his general theory of relativity. One of the first predictions of the new theory was that the curvature of space-time near a massive object like the Sun would produce exactly the extra precession that Le Verrier had measured. Mercury's anomalous orbit was one of the first confirmed predictions of general relativity. The smallest planet had played a role in one of the largest revisions in the history of human understanding of the universe. And still, almost nobody thought to look more closely at the planet itself. Most of what astronomers knew about Mercury's surface came from a single spacecraft that visited in the 1970s, and even that mission only photographed less than half the planet. The difficulty of reaching Mercury with a spacecraft made the data drought even worse. This is a point that surprises most people. They assume that because Mercury is close to the Sun, and therefore relatively close to Earth in absolute distance, it should be easy to get to. The opposite is true. Mercury is one of the hardest destinations in the solar system. The reason is orbital mechanics. Earth moves around the Sun at roughly 30 kilometers per second. Mercury moves at roughly 47 kilometers per second. To reach Mercury, a spacecraft launched from Earth must first fall inward toward the Sun, picking up speed as it drops deeper into the Sun's gravitational well. By the time it reaches Mercury's orbit, it is moving far too fast to stop. It would shoot past the planet and continue falling sunward unless it could somehow shed an enormous amount of velocity. Slowing down requires fuel. The amount of fuel needed to break into Mercury orbit from a direct transfer trajectory is staggering, more than what is needed to reach Jupiter in some mission profiles. The alternative is to use gravity assists, flying past other planets to gradually reshape the trajectory and bleed off speed over years of flight. This works, but it takes time. A lot of time. The result is that Mercury has been visited by fewer spacecraft than any other planet that has been visited at all. Mars has had dozens of orbiters, landers, and rovers. Venus has been mapped by radar from orbit. Jupiter and Saturn have had dedicated missions lasting years. Mercury, as of today, has been orbited by exactly one spacecraft in the history of human spaceflight. One. That spacecraft changed everything. But the gap between knowing Mercury was strange and understanding why it was strange lasted for more than 30 years. And during that gap, the simple picture, the boring picture, the assumption that Mercury was just a small dead rock with an oversized core and nothing else to say, hardened into common knowledge. Here is what that assumption missed. A planet with a core that large should, by most models, be geologically dead. Small bodies cool quickly, their interiors solidify. A planet Mercury's size should have lost its internal heat long ago, and with it, any chance of generating a magnetic field or driving geological activity. The Moon, which is roughly similar in size, has no global magnetic field. Mars, which is considerably larger, has only remnant magnetism frozen into ancient rocks, but no active dynamo. Mercury, the smallest of the 4 rocky planets, should, by every reasonable expectation, be magnetically silent. It is not. Mercury has a global magnetic field. It is weak, roughly 100 times weaker than Earth's, but it is there. It is a dipole field, meaning it has a north pole and a south pole like a bar magnet. And it is generated by the same fundamental process that creates Earth's field, a dynamo driven by the motion of liquid iron in the outer part of the core. This was first detected by Mariner 10 during its flybys in 1974 and 1975, and it immediately created a problem. The discovery did not fit the models. Planetary scientists had clear expectations for a body this size. A small planet cools from the outside in. The outer layers radiate heat into space. The interior follows. Over 4.5 billion years, a planet Mercury's size should have lost enough heat for its core to solidify entirely, shutting down any fluid motion and killing the dynamo. That is what happened on Mars. That is what happened on the Moon. That is what should have happened on Mercury. That means part of Mercury's core is still liquid. After 4.5 billion years, after all that time for a planet this small to cool and solidify, there is still enough heat and enough fluid motion in Mercury's interior to sustain an active magnetic dynamo. That fact alone should have elevated Mercury's status in planetary science decades ago. It means the planet's thermal history, the story of how its interior has cooled over time, is not the simple narrative of rapid heat loss that its size would suggest. Something is keeping Mercury's core at least partially molten. Something is sustaining convection in the liquid iron layer. Some researchers have proposed that the presence of lighter elements like sulfur in the core could lower the melting point of the iron alloy, keeping it liquid at temperatures where pure iron would have solidified. Others have suggested that the enormous size of the core relative to the mantle means heat escapes more slowly than standard models predicted, because the thin mantle is an inefficient radiator. The planet is, in a very real sense, still alive inside. And the mechanism keeping it alive is still debated. And the magnetic field itself is not just unexpectedly present, it is unexpectedly weird. When scientists mapped the field in detail, they found that it is not centered on the planet. The magnetic dipole is offset northward from Mercury's geometric center by roughly 480 kilometers, which is approximately 20% of the planet's entire radius. On Earth, the magnetic field is roughly symmetric around the equator, with modest variations. On Mercury, the field is dramatically lopsided. The northern hemisphere sits deeper inside the protective magnetic bubble than the southern hemisphere. The southern surface is more exposed to the solar wind, the stream of charged particles blasting outward from the sun at hundreds of kilometers per second. No simple model of a planetary dynamo predicted this offset. It implies that the convective patterns inside Mercury's liquid core are not symmetric. Something about the way heat escapes from the core, or the way the solid inner core interacts with the liquid outer core, or the way the thin mantle above conducts heat away, produces a dynamo that is fundamentally asymmetric. Understanding why is one of the open problems in planetary science. And then there is the surface. Mercury's surface looks ancient at first glance. It is covered in impact craters, some of them enormous. The Caloris Basin, one of the largest impact structures in the solar system, stretches more than 1,500 kilometers across. The cratered terrain resembles the lunar highlands, reinforcing the impression that Mercury is a dead world whose surface has not changed significantly in billions of years. But look closer. Amid the craters, there are vast, smooth plains, especially in the northern hemisphere, that are not ancient at all by geological standards. These plains are volcanic. They were created by enormous eruptions of lava that flooded low-lying areas and buried older terrain beneath kilometers of basalt. The scale of this volcanism is staggering. The northern volcanic plains alone cover an area larger than 60% of the continental United States, roughly 4.7 million square kilometers of terrain resurfaced by a single, extended episode of volcanic activity. The lava was not thick and sluggish. It flowed fast and far, filling in craters, lapping up against basin walls, smoothing the landscape into a flat expanse that contrasts sharply with the heavily cratered terrain surrounding it. Scientists estimate that this volcanic flooding occurred roughly 3.5 to 4 billion years ago, which means Mercury was geologically vigorous well into the first billion years of its life. Mercury did not just have a brief flirtation with volcanism early in its history. It experienced massive, sustained volcanic resurfacing that continued for a significant portion of its geological past. And the source of all that magma was the thin mantle, the same layer that looked too thin and too depleted to do much of anything. And the most unsettling detail of all, the one that most forcefully rejects the idea of Mercury as a simple dead world, is that the planet appears to be geologically active right now. Not volcanism, not in the present day, but something else. Mercury is shrinking, its interior is still cooling, still contracting, and as it does, the crust is being compressed. That compression creates thrust faults, places where one slab of crust is forced up and over another, producing cliff-like features called lobate scarps that stretch for hundreds of kilometers across the surface. Some of these scarps are enormous. Enterprise Rupes, the largest known, is roughly 1,000 kilometers long with more than 3 kilometers of vertical relief. It is comparable in length to the San Andreas Fault on Earth. The critical discovery came from the final phase of the Messenger mission, when the spacecraft was lowered to extremely low altitudes, skimming just tens of kilometers above the surface in its last months of operation. In those high-resolution images, scientists found small, fresh fault scarps, only a few kilometers long and tens of meters high. These scarps are so small and so pristine that they cannot be old. The constant bombardment of micrometeoroids would have erased them within tens of millions of years at most. Impact gardening, the process by which meteoroid strikes churn and fill in surface features, would have softened and buried these delicate structures long ago if they had formed early in Mercury's history. Their survival means they formed recently in geological terms, perhaps within the last 50 million years. A 2023 study in Nature Geoscience found hundreds of additional young grabens, small extensional fractures riding atop the older lobate scarps, distributed globally across Mercury's surface. The ages of these grabens were estimated at less than roughly 300 million years. Mercury is still contracting, still cracking, still tectonically active. It joins Earth as one of the only rocky bodies in the solar system where the crust is still being deformed by internal processes in the present geological era. A planet smaller than 2 moons. A planet that most people cannot describe beyond hot and small, and yet it has an active magnetic dynamo, a lopsided magnetic field that no model predicted, volcanic plains vast enough to bury a continent, and a crust that is still being reshaped by forces from within. The simple picture is not just incomplete, it was never close to the truth. And what happened next, when scientists finally got a spacecraft into orbit and began reading Mercury's chemistry element by element, was even more disorienting. Because the surface of Mercury turned out to be made of materials that should not exist on a planet that close to the Sun, the composition did not match the location, the geology did not match the size, and the features carved into the surface were like nothing anyone had ever seen on any world. The instruments were about to deliver a series of results that would break multiple theories at once. For more than 3 decades after Mariner 10's final flyby, Mercury sat in a kind of scientific limbo. The planet had been visited but not studied, photographed but not understood. Mariner 10 was a triumph of engineering for its era, the first spacecraft to use a gravity assist from one planet to reach another, swinging past Venus to bend its trajectory inward toward Mercury. It flew past the planet 3 times, in 1974 and 1975, snapping photographs and measuring fields and particles during each brief encounter. But each flyby lasted only minutes at close range. The geometry of the encounters meant the spacecraft saw roughly the same hemisphere of Mercury on all 3 passes. When the mission ended, less than 45% of the planet's surface had been imaged. The entire far side was a blank. What Mariner 10 did see was tantalizing. Alongside the craters and the magnetic field detection, it revealed something unexpected about Mercury's surface. There were smooth plains that did not look like simple crater-ejecta deposits. There were massive scarps cutting across the landscape, suggesting the planet had contracted at some point in its history. And the cratered terrain itself, while superficially lunar in appearance, was subtly different. The distribution of crater sizes did not perfectly match the Moon's. The spaces between large craters were smoother, as if something had resurfaced the intercrater regions, flooding them with material that buried smaller craters while leaving the larger ones intact. Mariner 10 scientists suspected volcanism, but could not prove it from flyby data alone. The spacecraft could not measure surface composition. It could not determine what the rocks were made of. It could not probe beneath the surface, and because it never entered orbit, it could not linger. What it did provide was enough to establish that Mercury was more than a simple lunar twin, that something had shaped this world beyond mere cratering. Those facts planted the seeds of curiosity. But without a follow-up mission, the seeds could not grow. The follow-up took 33 years. NASA's Messenger spacecraft, an acronym that stands for Mercury Surface, Space Environment, Geochemistry, and Ranging, launched in August of 2004. It would not reach Mercury orbit until March of 2011. 7 years of flight, not because Mercury is far away in absolute distance, but because the physics of getting there demands patience. Messenger performed 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself, each encounter carefully designed to reshape the spacecraft's orbit and shed velocity. The maneuver sequence was like a billiard trick played across hundreds of millions of kilometers. Each gravity assist bent the trajectory slightly, bled off a fraction of the excess speed, nudged the spacecraft closer to the orbital parameters it needed to be captured by Mercury's gravity. When Messenger finally settled into orbit, it became the first object built by humans to circle Mercury. The orbit was highly eccentric by design, swooping as close as 200 kilometers above the surface at its lowest point and climbing to more than 15,000 kilometers at its highest. This elliptical shape was partly dictated by the fuel constraints of reaching Mercury and partly by the need to keep the spacecraft from overheating. At its closest approach, Messenger passed over the northern hemisphere, which meant its instruments could study the north in far more detail than the south. The spacecraft carried 7 scientific instruments, including cameras, spectrometers for X-ray, gamma-ray, and neutron analysis, a magnetometer, a laser altimeter, and an atmospheric spectrometer. Over 4 years, it mapped the entire surface, measured the chemical composition of the rocks below, probed the magnetic field in 3 dimensions, and studied the thin haze of atoms that passes for Mercury's atmosphere. It collected more than 10 terabytes of data and returned more than 270,000 images. When its fuel ran out in April of 2015, mission controllers deliberately crashed it into Mercury's surface at roughly 3.9 kilometers per second, adding a small new crater, estimated at roughly 16 meters across, to the planet's collection. What Messenger found in those 4 years did not refine the existing picture of Mercury. It demolished it. Discovery after discovery arrived that contradicted what scientists expected, contradicted what the leading models predicted, and in several cases contradicted each other. The result was not a cleaner understanding of the planet. It was a deeper confusion, the kind that in science usually means you are finally asking the right questions. The first shock was the chemistry. Mercury orbits closer to the Sun than any other planet. The solar radiation at that distance is brutal. During formation, when the planet was assembling itself from the disk of gas and dust surrounding the young Sun, temperatures in Mercury's neighborhood should have been high enough to drive off volatile elements. Volatiles, in planetary science, are materials that evaporate or decompose at relatively low temperatures, things like water, sulfur compounds, alkali metals like sodium and potassium, and halogens like chlorine. The closer to the Sun you form, the fewer volatiles you should retain. That is a basic principle of planetary formation. It explains why the inner solar system is made of rock and metal, while the outer solar system is made of ice and gas. Mercury, sitting closest to the furnace, should be the most volatile, depleted, rocky planet of all. Messenger measured the opposite. The spacecraft's gamma-ray spectrometer and X-ray spectrometer mapped the abundances of key elements across Mercury's surface. The potassium to thorium ratio, a standard measure of how much volatile material a planet has retained, turned out to be comparable to that of Mars. Not depleted, not baked dry. Comparable to a planet that formed at more than 3 times Mercury's distance from the Sun. The surface contained potassium, sodium, and chlorine in concentrations that simply should not be there if Mercury formed in the searing heat of the innermost solar nebula. Then came the sulfur. Mercury's surface turned out to be extraordinarily rich in sulfur, with concentrations several times higher than those measured on Earth, Venus, or Mars. Sulfur is volatile. At the temperatures expected during Mercury's formation, it should have been driven off into space or prevented from accruing in the first place. Yet there it was, distributed broadly across the surface, mixed into the rocks, as if Mercury had formed in a region far cooler than its current orbit would suggest. At the same time, Messenger found that Mercury's surface is surprisingly low in iron. This seems paradoxical. Mercury is dominated by an iron core that constitutes roughly 70% of the planet's total mass, and yet the rocks on the surface contain less iron by weight than the surfaces of the Moon, Mars, or Earth. On the Moon, iron-bearing minerals darken the surface and give the mare basalts their characteristic grey-black color. On Mercury, the basaltic plains are lighter, the iron signature weaker. The combination is telling. It suggests that Mercury's iron sank almost entirely into the core during differentiation, the process by which a planet sorts its materials by density in its early molten phase. The silicate rocks that remained on the surface were iron-poor but sulfur-rich, a chemical fingerprint that does not match what any standard formation model for a planet at Mercury's orbital distance predicted. The high sulfur and low iron together also tell scientists something crucial about the oxygen content of the material from which Mercury formed. On Earth and Mars, iron combines readily with oxygen to form iron oxides. On Mercury, the surface chemistry suggests that oxygen was far less abundant in the original building materials. Instead of iron oxides, Mercury's rocks contain iron sulfides and other reduced compounds, minerals that form in oxygen-poor environments. This is a fundamentally different chemical regime from the other rocky planets. It implies that Mercury formed from source materials with a different oxidation state, materials that were chemically distinct from those that built Earth, Venus, or Mars. The inner solar system was not a uniform mix. It was chemically stratified, and Mercury preserves the signature of the innermost, most reduced layer. Each of these chemical results carried the same message. Mercury did not form the way the models said it should have. Specifically, these results attacked the giant impact hypothesis directly. Remember, the leading explanation for Mercury's oversized core was that a catastrophic collision had stripped away most of the silicate mantle, leaving behind the dense metallic interior. If that were true, the violence of the impact would have released tremendous energy, enough to vaporize rock, superheat the remaining material, and drive off virtually all volatile elements. A post-impact Mercury should be volatile dead. The potassium should be gone. The sodium should be gone. The sulfur and chlorine should be long since baked into oblivion. Messenger found all of them present in healthy abundances. This was not a minor revision to the theory. It was a fundamental contradiction. The giant impact that explains the core cannot easily coexist with the volatile chemistry that exists on the surface. The two observations pull in opposite directions. Scientists have proposed workarounds. Perhaps the impact happened at low enough velocity that some volatiles were retained. Perhaps volatile-rich material was delivered to Mercury's surface later by comets or asteroids. Perhaps the impact was a grazing collision rather than a head-on one, energetic enough to strip silicates but not hot enough to fully devolatilize the remnant. Each workaround creates its own problems, and none has been universally accepted. The tension between Mercury's structure and Mercury's chemistry remains one of the central unresolved problems in planetary science. But the chemistry was only the beginning of the strangeness. Messenger found features on Mercury's surface that had never been seen on any world in the solar system. They are called hollows. The name is deliberately modest. When scientists first saw them in Messenger's high-resolution images, they did not know what to call them. They are shallow, flat-floored, irregular depressions scattered across Mercury's surface. They have no raised rims. They do not look like impact craters. They do not look like volcanic vents. They cluster inside and around impact craters, particularly on crater floors and central peaks, often appearing in dense groups that give the terrain a pitted, etched appearance. Individual hollows range from tens of meters to over a kilometer across and are typically only about 20 to 40 meters deep. Their brightness is what first caught scientists' attention. Hollows are among the brightest features on Mercury's surface. In enhanced color images from Messenger, They glow a distinctive bluish-white against the surrounding darker terrain, like patches of frost on dark stone. That brightness comes from fresh, unweathered material exposed at their edges, material that has not yet been darkened by the relentless bombardment of micrometeorites and solar wind particles that gradually darkens everything on Mercury's surface, and that is the critical clue. The freshness of the hollows indicates that they are young, possibly still forming today. The leading explanation is that hollows form through the loss of volatile materials from the surface. When an impact crater excavates deep into Mercury's crust, it brings up material from below that is rich in volatile compounds, possibly sulfur-bearing minerals or other substances that are unstable when exposed to Mercury's extreme surface conditions. Once that material is exposed to the full fury of solar radiation, the dayside heat, the solar wind, and micrometeoritic bombardment, the volatile component begins to sublimate or decompose, escaping into space and leaving behind a weakened, porous residue that collapses into the shallow depressions we see as hollows. This process has no known analog on any other body in the solar system. The Moon has no hollows. Mars has nothing similar. The mechanism requires a specific combination of conditions that appears to be unique to Mercury, a surface rich in volatiles that are stable underground but unstable when exposed, coupled with the extreme thermal and radiation environment of the innermost planet. The hollows are not just a geological curiosity. They are direct evidence that Mercury's crust contains significant volatile material right now, today, and that this material is actively being lost to space in a process that is reshaping the surface in real time. Think about what that means for a moment. Mercury, the planet everyone assumed was baked dry by the sun, has a crust loaded with volatile compounds. Those compounds are close enough to the surface that impacts routinely bring them up. And once exposed, they are escaping, creating landforms that did not exist a few million years ago. The surface of Mercury is changing while we watch, not on a geological timescale of hundreds of millions of years. On a timescale that is, by planetary standards, practically yesterday. Messenger catalogued over 400 groups of hollows spread across the planet. They occur at virtually every latitude and longitude. They are not confined to one region or one type of terrain. They are everywhere, which means the volatile-bearing material beneath the surface is everywhere. Mercury's crust is not the desiccated, depleted shell that the planet's proximity to the sun would predict. It is a reservoir of unstable chemistry, slowly leaking into space, one hollow at a time. And then there was the ice. This is the discovery that tends to make people do a double take. Water ice. On Mercury, the planet where the dayside temperature exceeds 400 degrees Celsius. The planet that orbits closer to the sun than anything else. That Mercury has ice. The evidence had been building since the early 1990s. When Earth-based radar observations from the Arecibo Observatory detected highly reflective patches near Mercury's north and south poles, the radar signatures were consistent with water ice. But the detections were ambiguous. Other materials can produce similar radar reflections. Without a spacecraft in orbit to check, the claim remained provisional. Messenger confirmed it. Using its neutron spectrometer, the spacecraft detected hydrogen-rich deposits in permanently shadowed craters near the North Pole. The measurement works because water molecules contain hydrogen, and hydrogen affects the energy of neutrons scattered from the surface in a characteristic way. The signal was unambiguous. There is hydrogen, almost certainly in the form of water ice, sitting in the floors of craters near Mercury's poles where the sun never shines. The geometry that makes this possible is elegant. Mercury's axis of rotation is nearly perpendicular to its orbital plane, tilted by less than 1/10 of a degree. This is the smallest axial tilt of any planet in the solar system. It means that at the poles, the The sun always sits very close to the horizon. The rims of deep impact craters at high latitudes cast permanent shadows on their floors. Sunlight has never reached those crater floors in billions of years. Without an atmosphere to carry heat, the temperatures in those permanent shadows can drop to roughly negative 170 degrees Celsius. Cold enough for water ice to remain stable over geological time, Messenger's laser altimeter mapped the topography of these craters and the thermal models matched perfectly. The locations of the radar-bright deposits corresponded exactly to areas of permanent shadow. The deposits in some craters appeared to be exposed ice sitting right on the surface. In other craters, the ice appeared to be buried beneath a thin layer of dark material, roughly 10 to 20 centimeters thick, possibly organic compounds delivered alongside the water by comet or asteroid impacts. This dark layer is significant. It is darker than the already dark surrounding terrain, darker, in fact, than most surfaces in the solar system. Some scientists have suggested it contains complex carbon-bearing molecules, tars, and organic residues baked by radiation over billions of years into a thin crust that insulates and protects the ice beneath. If that interpretation is correct, then Mercury's polar craters contain not just water ice, but a layer of concentrated organic chemistry, the raw ingredients of prebiotic processes, preserved in the most unlikely of locations. That dark, insulating layer would protect the ice from sublimation, even if temperatures occasionally crept slightly above the stability threshold. The ice beneath it could persist for billions of years, accumulating gradually from cometary deliveries and possibly from volcanic outgassing early in Mercury's history. The volume of ice is not trivial. Estimates based on messenger data and radar observations suggest that Mercury's polar ice deposits could contain somewhere on the order of tens of billions of metric tons of water ice, though the true figure could be considerably higher or lower depending on the thickness of the deposits, which remains poorly constrained. Even at the conservative end, this is far more than a thin frost. It is a substantial reservoir of water ice locked in the permanent shadows of the hottest planet's frozen craters. The irony is almost too perfect. The same planet that reaches temperatures capable of melting lead on its sun-facing side also harbors one of the most pristine reserves of water ice in the inner solar system, hidden in the only places the sun cannot reach. Mercury does not choose between extremes, it holds both simultaneously. The ice also carries implications for the planet's history. Where did the water come from? The two leading sources are cometary impacts and outgassing from Mercury's interior. If comets delivered the water, it means Mercury has been accumulating volatile material from external sources for billions of years, building up its polar deposits one impact at a time. If the water came from inside the planet, released through volcanic outgassing early in Mercury's history, it means Mercury's interior was once rich in water, another blow to the idea that the planet formed in a dry, superheated zone close to the sun. Either way, the presence of the ice adds to the same overarching story. Mercury is not the volatile, depleted world it was supposed to be. There is one more discovery from Messenger that rarely gets the attention it deserves. But it rounds out the picture of a planet that is far more dynamic than anyone expected. Mercury has a tail. Not a cometary tail, not a stream of debris. A tail of sodium atoms streaming away from the planet in the anti-sunward direction, pushed by the pressure of sunlight itself. Mercury's exosphere, the sparse collection of atoms hovering above the surface, is primarily composed of sodium, calcium, magnesium, and potassium. These atoms are liberated from the surface by a combination of processes: solar wind, sputtering, where charged particles from the sun slam into the surface at hundreds of kilometers per second and knock atoms loose from mineral lattices; photodesorption, where solar ultraviolet photons provide enough energy to free weakly bound atoms from mineral surfaces, micrometeorite vaporization, where tiny high-speed impacts blast surface material into vapor, and possibly thermal desorption from the hottest parts of the dayside surface, where temperatures are high enough that some atoms simply shake loose from the crystal structures that hold them. Once these atoms are free, they are no longer bound to the surface. Mercury's gravity is weak enough, and the radiation pressure from sunlight is strong enough that the atoms can be accelerated away from the sun. The sodium atoms, in particular, scatter sunlight efficiently at a specific orange wavelength near 589 nanometers, making Mercury's sodium tail visible to telescopes on Earth as a faint amber glow streaming behind the planet. The tail extends hundreds of thousands of kilometers downstream, a ghostly exhalation of surface material being stripped away atom by atom. On occasion, when conditions are right, amateur astronomers with modest telescopes have even imaged the tail during Mercury's passage across the sky. Messenger's Mercury atmospheric and surface composition spectrometer tracked this tail extensively and found that it varies with Mercury's distance from the Sun. When Mercury is at perihelion, closest to the Sun, the solar wind is more intense, sputtering is stronger, and the tail brightens. When Mercury is at aphelion, farthest from the Sun, the tail fades. The entire system pulses in rhythm with Mercury's eccentric orbit, the planet breathing out atoms of its own surface in a cycle driven by the star it cannot escape. This sodium tail is not just a curiosity. It is evidence of an ongoing process of surface erosion and atmospheric replenishment that operates continuously. Mercury is losing material to space right now. Its surface is being slowly chipped away by the Sun, and the composition of the exosphere tells scientists something about the composition of the surface itself, because the atoms being knocked loose are the atoms that make up the rocks below. The exosphere is a window into Mercury's chemistry, a stream of information carried away from the planet on the solar wind. Put all of these discoveries together, and the picture that emerges is almost the opposite of the one people carry in their heads. Mercury is not a dead rock. It is a world with a partially liquid core sustaining a dynamo, a surface loaded with volatile compounds that should have been baked away. Mysterious hollows that are actively forming and reshaping the terrain. Billions of tons of water ice locked in permanent shadows at the poles. A sodium tail, hundreds of thousands of kilometers long, pulsing in time with the planet's orbit. And a crust that is still cracking under the stress of a cooling, contracting interior. Messenger's principal investigator, Sean Solomon, described the experience of studying the data as one of persistent surprise. Every instrument returned results that challenged at least one established expectation. The mission did not confirm the textbook version of Mercury. It proved the textbook was wrong, and yet for all it revealed, Messenger also exposed the limits of what a single spacecraft, with a particular set of instruments in a particular orbit, could learn. Messenger's orbit was highly elliptical, bringing it close to the surface in the northern hemisphere, but keeping it at much higher altitudes over the south. The result was a severe asymmetry in data quality. The North Pole region was mapped in exquisite detail. The South Pole and much of the southern hemisphere remained comparatively blurry, with lower resolution images and less precise compositional data. The hollows, the fault scarps, the ice deposits, all were characterized far better in the north than in the south. Any conclusions drawn from the data carried the asterisk that they were based on an incomplete picture, MESENGR, also could not directly measure Mercury's interior density structure with the precision needed to definitively constrain the core's composition. It could not determine exactly how much of the core is liquid and how much is solid. It could not map the global distribution of sulfur and other volatiles at the resolution needed to distinguish between competing formation models. It could not determine whether the hollows are forming at the same rate everywhere, or whether certain regions are more active than others. And it could not answer the question that every discovery it made pointed toward. The question that sits at the center of Mercury science, like the iron core, sits at the center of the planet. How did Mercury become this? The giant impact hypothesis was the best answer anyone had, and Messenger's chemical data severely wounded it. But nothing had risen to take its place. The volatile abundance, said Mercury, could not have formed the way the impact model required. The core size said something extraordinary had happened to Mercury's interior. The magnetic field said the core was still partially liquid, despite 4.5 billion years of cooling. The hollows said the crust was full of unstable material that was leaking into space. And none of these observations pointed cleanly toward a single alternative explanation. What they pointed toward was a planet whose origin story was genuinely unknown. Not unknown in the casual sense of we have not figured it out yet. Unknown in the deeper sense of we do not currently possess a model that accounts for all of the evidence simultaneously. That is a rare and important state in planetary science. It means Mercury is not a solved problem waiting for a few details to be filled in. It is an open problem, one of the most significant in the study of rocky planet formation. The data sits in the archives, 10 terabytes of measurements, hundreds of thousands of images, spectral maps of a world that refuses to match any single theory. And the competing theories that have emerged to fill the gap left by the wounded impact model are as different from each other as the scientists who propose them. Some point to the sun's magnetic field. Some point to the chaos of the early solar system. Some point to processes in the protoplanetary disk that sorted materials before the planets even began to form. Each theory explains part of Mercury. None explains all of it. The race to explain Mercury is still running. The finish line is not yet in sight. And the next wave of answers will not come from old data reanalyzed. It will come from a spacecraft that is, right now, approaching Mercury on its final trajectory, carrying instruments designed to see what Messenger could not. But first, we need to understand what the theorists have been building while the engineers were flying. Science has a specific term for the situation Mercury created. It is called an underdetermined problem. You have more unknowns than equations. The data constrains the answer, but does not uniquely determine it. Multiple solutions fit parts of the evidence. None fits all of it. And every time new data arrives, instead of narrowing the possibilities, it seems to widen them. Mercury's formation has been in this state for over a decade, and the theories competing to explain it have grown more sophisticated, more creative, and more contradictory. The story starts with the theory that held the field for the longest time. The giant impact hypothesis was the original answer to the Mercury problem, and understanding why it dominated for so long is essential to understanding why its decline created such a vacuum. The idea goes back to the 1980s. Scientists looked at Mercury's enormous iron core and its thin silicate shell and asked what could produce such extreme proportions. The cleanest explanation was subtraction. Start with a larger planet, one that originally had a normal rock-to-iron ratio similar to Earth or Venus. Then remove most of the rock. What is left behind is a planet that is almost all core. And the most obvious mechanism for removing rock from a planet in the early solar system is a collision. The inner solar system 4.5 billion years ago was a demolition arena. Dozens of planetary embryos, bodies ranging from the size of the Moon to the size of Mars, were careening through overlapping orbits, crashing into each other, merging, fragmenting, and reshaping themselves through violence, on a scale that is almost impossible to visualize. Every rocky planet we see today is the survivor of this period. Earth itself was struck by a Mars-sized impactor that is believed to have created the Moon. The idea that Mercury suffered a similar collision was not exotic, it was expected. The only question was the details. The original models, developed by Willy Benz and colleagues, simulated a head-on collision between a proto-Mercury roughly 5 times its current mass and a body roughly 1/6 that mass, moving at speeds of roughly 20 kilometers per second or more. The impact was catastrophic. The kinetic energy converted into heat in a fraction of an hour. Rock was vaporized. The silicate mantle was blasted outward in a spray of molten and gaseous debris. Some of that debris achieved escape velocity and was lost to interplanetary space. Some went into orbit around the Sun and was eventually swept up by other bodies or dispersed. What remained was the iron core, largely intact because of its higher density and greater resistance to dispersal, surrounded by a thin, surviving film of silicate material. The simulations produced a body whose core fraction matched Mercury's. The physics worked, the math checked out. The model was elegant, dramatic, and satisfying. For decades, the giant impact was the answer. The problems began piling up slowly and then all at once. The first problem was efficiency. Later, more detailed simulations showed that a single head-on impact of the type Benz modeled was extraordinarily difficult to achieve in practice. The collision had to happen at just the right angle, just the right speed, with just the right mass ratio. Too slow, and the two bodies would merge rather than strip material away. Too fast, and both bodies would be destroyed entirely. Too oblique, and the impactor would deliver a glancing blow that reshapes the target without removing enough mantle. The window of conditions that produces a Mercury-like outcome was narrow. Not impossible, but narrow enough that it raised the question of whether invoking such a specific event was really an explanation or just a re-description of the problem. A study published in 2024 by Du and colleagues at the University of Bristol modeled the giant impact scenario with modern computational methods and concluded that a single giant impact is unlikely to be energetic enough and efficient enough to strip sufficient mantle material to produce Mercury's core mass fraction of approximately 0.7. The silicate material ejected during the collision does not simply vanish. It goes into orbit around the Sun. Some of it reaccretes onto Mercury over the following millions of years, partially rebuilding the mantle that the impact removed. When you account for this reaccretion, the net effect of even a large impact is smaller than the original models assumed. You strip away rock, but then gravity feeds some of it back. The final planet ends up with a lower core fraction than the impact alone would suggest. Then came Messenger's volatile data, and the damage became severe. As we have already seen, Mercury's surface retains potassium, sodium, sulfur, and chlorine in abundances that no high-energy stripping event should have left behind. The chemistry and the structure pointed in opposite directions. The core demanded violence. The surface chemistry demanded restraint. No single version of the impact model could satisfy both demands at once. The contradiction was not subtle. It sat at the center of Mercury science like a crack in a load-bearing wall. Scientists attempted to rescue the impact hypothesis with modifications. Perhaps the impact occurred at lower velocity than originally modeled. Perhaps the angle was more oblique, spreading the energy over a longer duration and reducing peak temperatures. Perhaps volatile-rich material was delivered to Mercury after the impact by later bombardment from comets and asteroids, restocking the surface with the very elements the collision had removed. Each modification helped with one problem while creating another. A lower velocity impact is less efficient at removing mantle material, making it harder to reach Mercury's core fraction. An oblique impact preserves more volatiles but strips less rock. Post-impact volatile delivery requires a specific and sustained bombardment history that is difficult to constrain and impossible to confirm with current data. The giant impact hypothesis was not killed by a single observation. It was weakened by the accumulation of difficulties until the weight of the caveats nearly equaled the weight of the original explanation. Into this gap stepped a set of alternative theories, each approaching the problem from a fundamentally different direction. The first alternative came from an unexpected source, not planetary science, but geochemistry. In 2021, William McDonough at the University of Maryland and Takashi Yoshizaki at Tohoku University published a model that proposed a completely different origin for Mercury's oversized core. Their idea had nothing to do with collisions. It had to do with the Sun's magnetic field. The concept begins with the protoplanetary disk, the vast rotating cloud of gas and dust from which the planets formed. This disk was not uniform. It had temperature gradients, pressure gradients, and composition gradients that varied with distance from the young Sun. McDonough and Yoshizaki added another variable that previous models had largely ignored: magnetism. The young Sun was magnetically active, far more so than it is today. Its magnetic field extended into the surrounding disk and interacted with the materials there. Iron grains in the disk, being metallic and therefore responsive to magnetic fields, would have been drawn preferentially toward the inner regions of the disk, closer to the Sun. Silicate grains, being non-metallic, would not have experienced the same pull. The result was a sorting process that operated before the planets ever formed, concentrating iron in the inner disk and depleting it from the outer disk. When planets began to assemble from these sorted materials, the ones closest to the Sun naturally incorporated more iron. Mercury, forming from the most iron-enriched zone, would have been born with an oversized core as a fundamental feature of its composition, not as the scar of a later catastrophe. The model predicts a gradient in metal content across the inner solar system, with iron fraction decreasing as you move outward. Mercury should be the most iron-rich. Earth and Venus should be intermediate. Mars should be the most iron-poor. This prediction matches reality. Mercury's core is roughly 70% of its mass. Earth and Venus are roughly 30 to 33%. Mars is roughly 25%. The gradient is clean and consistent. McDonough and Yoshizaki argued that this match is not a coincidence. It is the signature of the Sun's magnetic field imprinted on the architecture of the solar system itself. The elegance of the model is considerable. It explains Mercury's iron abundance without requiring any unusual event. No special collision, no lucky accident, just the physics of magnetic fields acting on metallic grains in a dusty disk. And because the model does not invoke a high-energy impact, it does not face the volatile retention problem. Mercury could have formed cool enough to retain potassium, sulfur, and the other volatile elements that MESSENGER detected. The chemistry and the structure are explained by the same mechanism, but the model has limitations. It explains the bulk iron content well, but it is less clear about the specific details of Mercury's interior structure, the thin mantle, the still liquid outer core, the asymmetric magnetic field. A planet that simply accreted more iron from the disk might have a large core, but would it necessarily have the particular internal layering that Mercury exhibits? The model describes the ingredients, but does not fully prescribe the architecture that resulted from assembling them. And there is a practical limitation that McDonough himself acknowledged. We currently have no way to measure the magnetic properties of other stars from Earth-based observations. This means the model cannot be directly tested against exoplanetary systems. It fits our solar system beautifully, but we cannot yet confirm whether it is a universal rule or a local coincidence. The second alternative takes the collision idea and reinvents it. Instead of throwing the giant impact out entirely, a group of researchers asked whether the problem was not with the idea of a collision itself, but with the type of collision that was being modeled. In 2025, a study modeled what happens when two planetary embryos of similar size collide at a grazing angle rather than head-on. This is called a hit-and-run collision, and it is actually more common in the chaotic environment of the early inner solar system than the head-on impacts that the original Mercury models assumed. When two bodies of comparable mass approach each other on a near-miss trajectory, they interact violently, but briefly. The smaller body passes through the gravitational influence of the larger one, is distorted and partially stripped, and then escapes back into its own orbit rather than merging with the larger body. The encounter is traumatic but not fatal. The smaller body survives, bruised and diminished, with a portion of its outer layers torn away. The researchers showed through simulations that a series of these grazing encounters could progressively strip mantle material from proto-Mercury without ever reaching the extreme. Temperatures of a head-on impact. Each hit-and-run removes a fraction of the silicate shell. The stripped material does not disappear. It is scattered into nearby orbits where it may be accreted by other growing planets, a detail that led the researchers to a striking suggestion. Some of Mercury's missing mantle may have ended up inside Earth or Venus. The rocky material that was stripped from proto-Mercury during these encounters could have been swept up by the larger planets growing nearby, incorporated into their mantles without a trace. If true, pieces of the planet we overlook may be buried inside the planet we stand on. Over several encounters, the cumulative loss from Mercury is enough to produce its current core fraction. And because each individual encounter is less energetic than a single giant impact, the peak temperatures are lower. This means volatile elements have a better chance of surviving the process. The hit-and-run model threads the needle between the structural evidence, which demands significant mantle loss, and the chemical evidence, which demands that the mantle loss was not too violent. The researchers were careful to note that their model does not directly solve the volatile problem in its entirety. Even a series of grazing impacts would have removed some volatile material, but the model is compatible with a secondary process of volatile redelivery by later impacts from comets or volatile-rich planetesimals. The combination, partial stripping by hit-and-run collisions followed by partial restocking by later bombardment, is physically plausible and produces outcomes broadly consistent with what Messenger observed. The hit-and-run model also has an intriguing structural implication. The researchers noted that the simulations produce Mercury-like bodies without requiring exceptional or improbable collision geometries. Hit-and-run interactions between similarly sized embryos are a natural and common outcome of planet formation simulations. This means Mercury's formation does not require a 1 in a billion stroke of bad luck. It could be a normal consequence of the gravitational chaos that shaped the inner solar system. Mercury is strange, but it may not be a freak. The third alternative takes the broadest view of all. In late 2025, Hania Taja and colleagues published the results of N-body simulations, computational models that track the gravitational interactions and collisions of thousands of growing planetary bodies, designed to test whether Mercury-like planets can emerge naturally from the process of planet formation without invoking any specific event. Their approach was to set up the protoplanetary disk with different initial conditions, and then let gravity, collisions, and accretion play out over hundreds of millions of simulated years. When they started with a uniform composition, giving every particle in the disk the same rock-to-iron ratio, the simulations failed to produce anything resembling Mercury. The growing planets always ended up with core fractions near 0.3 to 0.4, similar to Earth. Collisions occurred, but their effects averaged out. Iron-rich fragments produced by impacts were later swallowed by bodies with normal compositions, diluting the signal. But when Taja's team introduced a step function in the initial composition, an inner zone of the disk enriched in iron and an outer zone dominated by silicates, reflecting the kind of chemical gradient that McDonough's magnetic sorting would produce, Mercury-like planets emerged naturally. Bodies forming in the iron-rich inner zone accreted high-metal material from the start and maintained elevated core fractions through the entire growth process. The simulations produced planets with core mass fractions of 0.5 to 0.7, overlapping with Mercury's observed value. The results reinforced a growing consensus. Mercury's iron heart is probably not the result of a single dramatic event. It is more likely a consequence of the chemical conditions that prevailed in the inner solar nebula before planet formation even began. The raw materials were iron-rich from the start. Mercury did not become metal-heavy. It was born that way. This conclusion gains additional weight from a discovery that extends Mercury's story beyond our solar system entirely. Astronomers studying exoplanets, planets orbiting other stars, have identified a growing population of dense, iron-rich worlds that appear to share Mercury's unusual composition. These exomercuries, as researchers have begun to call them, orbit close to their host stars and have densities that imply core mass fractions far higher than Earth-like values. The existence of these objects is significant because it suggests that Mercury-like formation pathways are not unique to our system. They appear to be a natural outcome of rocky planet formation in the inner regions of protoplanetary disks, regardless of which specific star or disk is involved. If Mercury were truly the product of a one-time freak collision, you would not expect to find similar objects around other stars unless every one of those systems also happened to experience a similar freak collision. The more exomercuries astronomers find, the harder it becomes to explain all of them through random impacts. The simpler explanation is that the conditions in the inner regions of many protoplanetary disks naturally produce iron-enriched building materials, and planets formed from those materials naturally end up with oversized cores. Mercury is not an accident. It may be an archetype, but the N-body simulations also revealed a persistent problem that no model has fully solved. The Mercury-like planets they produced were consistently too massive. They had the right core fractions but the wrong total mass. Real Mercury is tiny, with a mass of only about 5.5% of Earth's. The simulated analogues were typically several times heavier. Getting both the composition and the size right in a single simulation has proven extraordinarily difficult. Some mechanism must have limited Mercury's growth or removed mass after it formed, and identifying that mechanism is one of the major open questions in the field. It is possible that gravitational perturbations from other growing planets stunted Mercury's accretion. It is possible that the gas disk dispersed before Mercury could gather more material. It is possible that some combination of the above theories is needed. Iron enrichment from disk chemistry, combined with partial mantle loss from moderate collisions. The truth may not be any single theory, but a hybrid of several. There is a fourth idea that does not fit neatly into any of the above categories, and it comes from an unexpected piece of evidence. Remember the potassium to thorium ratio that Messenger measured on Mercury's surface. That ratio does not just indicate volatile retention. It provides an estimate of the temperature at which a planet formed. Mercury's ratio is not consistent with formation in the scorching inner disk where it currently orbits. It points to a cooler origin, possibly as far from the Sun as Mars, or even beyond. This has led some scientists to propose that Mercury did not form where it is now. It may have formed farther out in the solar system, in a cooler region where volatiles were more abundant, and then migrated inward to its current orbit through gravitational interactions with other planetary embryos, or with the dissipating gas of the protoplanetary disk. Inward migration is a well-documented phenomenon in planet formation theory. It happens routinely in simulations and is believed to have occurred for several planets in our system. Jupiter is thought to have migrated inward and then outward again in a process called the Grand Tack, reshaping the orbits and masses of the inner planets in the process. If Mercury formed beyond Mars and was later scattered inward by gravitational encounters with the growing terrestrial planets, it would explain both the volatile retention and the ion enrichment, the ion from the magnetic sorting of the inner disk through which it passed, the volatiles from the cooler conditions of its original birthplace. The scenario also offers a potential explanation for Mercury's small size. A planet that migrated inward through a region already depleted by the formation of Earth and Venus would have had little remaining material to accrete. Its growth would have been stunted not by some intrinsic property, but by the simple fact that the cupboard was bare by the time it arrived at its current address. This idea is speculative and difficult to test directly, but it is not fringe. Johannes Benkoff, the project scientist for the Bepi-Colombo mission, has discussed it publicly as one of the scenarios that Bepi-Colombo's data could help evaluate. If Mercury's detailed surface mineralogy shows signatures consistent with formation in a cooler environment, it would support the migration hypothesis. If the mineralogy is consistent with local high-temperature formation, it would argue against it. And this brings us to the reason the theoretical debate cannot be settled from Earth. The competing models make different predictions about Mercury's detailed composition, interior structure, and surface mineralogy. But the measurements needed to discriminate between them require a spacecraft in orbit, with instruments capable of global mapping at higher resolution and across a broader range of wavelengths than Messenger could achieve. Messenger opened the door. It revealed the contradictions, but it did not carry the tools to resolve them. That spacecraft now exists. It has been flying for over 7 years. It has already completed 6 flybys of Mercury, each one returning data that scientists are still analyzing. And it is now on its final approach. Bepi-Colombo is a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency. It consists of 2 orbiters stacked together for the journey and designed to separate upon arrival. The Mercury Planetary Orbiter, built by ESA, carries 11 instruments focused on surface composition, geology, interior structure, and the gravitational field. The Mercury Magnetospheric Orbiter, called MEO, built by JAXA, carries 5 instruments focused on the magnetic field, the magnetosphere, and the interaction between Mercury and the solar wind. The mission was launched in October of 2018. Its trajectory required 1 flyby of Earth, 2 flybys of Venus, and 6 flybys of Mercury, each one bleeding off velocity and reshaping the orbit. A thruster issue discovered in 2024 forced a revised trajectory that added approximately 1 year to the cruise phase. The problem involved the spacecraft's electric propulsion system, which could not operate at full power, requiring mission planners to redesign the final approach using a trajectory that relies more heavily on gravitational braking and less on engine thrust. Bepi-Colombo completed its 6th and final Mercury flyby in January of 2025, passing just 295 kilometers above the surface and imaging the permanently shadowed craters near the North Pole where Messenger had detected water ice. The monitoring cameras captured views of the Caloris Basin, the vast northern plains, and several deep polar craters, including Prokofiev and Kandinsky. providing tantalizing previews of the terrain the orbiters will study in detail once the science mission begins. The spacecraft is now scheduled to enter Mercury orbit in November of 2026, with full science operations beginning in early 2027. During the flybys, Bepi Colombo's instruments have already returned new data. The Mertis spectrometer, a thermal infrared imaging instrument developed by the German Aerospace Center, observed Mercury in mid-infrared light for the first time during the fifth flyby in December of 2024. Mid-infrared observations are crucial for identifying minerals on the surface because different minerals emit thermal radiation at characteristic wavelengths. Messenger did not carry a mid-infrared spectrometer. Bepi Colombo's ability to map Mercury's mineralogy in this wavelength range is one of its most significant advantages over its predecessor. Once in orbit, Bepi Colombo will address the formation debate from multiple angles simultaneously. Its X-ray spectrometer will map the global distribution of major and trace elements at higher resolution than Messenger achieved, particularly in the southern hemisphere, which Messenger mapped poorly due to its orbital geometry. Bepi Colombo's two orbiters will be in complementary polar orbits, ensuring full global coverage for the first time. The laser altimeter will map the topography with precision sufficient to resolve the internal density structure when combined with gravitational data from the radio science experiment. Together, these measurements will constrain the size and state of Mercury's inner core, the thickness of the liquid outer core, and the density of the mantle. The fundamental parameters that every formation model must match. The magnetometer suite, carried on both orbiters, will map Mercury's magnetic field with a level of detail that Messenger could not approach. MEO will fly through the outer magnetosphere, while the MPO orbiter hugs the surface below it. The combination means that for the first time, scientists will be able to separate the internal dynamo signal from the external noise of the solar wind and determine whether the northward offset of the magnetic dipole reflects a deep asymmetry in core convection or a shallower effect in the mantle above it. The answer will constrain not just Mercury's present structure, but the thermal history that produced it. The stakes are not small. Mercury is not just a puzzle for its own sake. It is the test case for our understanding of how rocky planets form in the inner regions of stellar systems. Each competing theory carries implications that extend far beyond one small world, implications for how we interpret the hundreds of dense, iron-rich exoplanets now being catalogued around other stars, and for how confidently we can claim to understand the process that built our own Earth. The answer Mercury eventually gives will rewrite not just its own chapter, but chapters we thought were already finished. The data will begin arriving in 2027. The formation debate that has been running for 4 decades may finally reach a turning point. But whatever Bepi Colombo finds, one thing is already clear. The answer will not be simple. Mercury has never rewarded the assumption of simplicity. Every time a spacecraft has looked closer, the planet has become stranger. Every time a theorist has proposed a clean explanation, the data has introduced a new wrinkle. And that is perhaps the deepest lesson Mercury has been teaching all along. Not just about itself, but about the nature of planetary science. The question now is not just how Mercury formed. It is what Mercury's existence tells us about every other rocky world in the universe, about the inner zones of protoplanetary disks we have never visited, about the small, dense planets we are finding around other stars. Mercury is the Rosetta Stone for a class of worlds we are only beginning to discover. And that question reaches far beyond any single planet. When Bepi Colombo's 2 orbiters finally separate and settle into their respective orbits around Mercury, something will change that has not changed since Messenger's fuel ran out in 2015. There will be instruments at Mercury again, not passing through, not snapping photographs during a brief flyby. orbiting, measuring, mapping continuously. And the data that begins flowing back will not just fill gaps in the existing picture. If the pattern of Mercury science holds, it will redraw the picture entirely. It will not arrive in a single dramatic revelation. It will come in streams, weeks and months of measurements that accumulate into maps, profiles, and spectra. Scientists will build those streams into a picture of Mercury's surface composition, hemisphere by hemisphere, element by element, with a completeness that Messenger could not achieve. The southern hemisphere, which Messenger mapped at relatively low resolution because of its eccentric orbit, will finally receive the same scrutiny as the north. For the first time, researchers will have a truly global view of the planet's chemistry. And the differences between north and south may turn out to be as revealing as anything else Mercury has to offer. Messenger showed that Mercury's north is dominated by vast volcanic plains, smooth terrain that buried older craters under kilometers of basalt. The south, by contrast, is ancient and heavily cratered, a surface that appears to have escaped the large-scale volcanic resurfacing that transformed the north. The magnetic field mirrors this asymmetry, offset northward from the planet's center by hundreds of kilometers. Whether the geological asymmetry and the magnetic asymmetry are connected, whether the processes inside the planet that produce a lopsided dynamo also drove preferential volcanism in the north, is one of the questions Bepi Colombo was specifically designed to address. The mineralogy data will be critical. Messenger could identify elements on the surface, but was limited in its ability to identify specific minerals, the crystalline structures in which those elements are arranged. Minerals carry information about the conditions under which they formed. A rock's mineral assemblage tells you the temperature, the pressure, the oxygen content, and the cooling history of the environment where it solidified. Bepi Colombo's thermal infrared spectrometer will measure these mineral signatures across the globe, producing a map not just of what Mercury is made of, but of how those materials came together. If the minerals indicate formation under reducing conditions, low in oxygen and rich in sulfur across the entire planet, it will support the idea that Mercury formed from chemically distinct building materials. If the mineralogy varies between regions, it could indicate a more complex history involving multiple sources of material or multiple episodes of geological processing. The interior structure measurements may be the most consequential of all. By tracking the precise orbit of the Mercury planetary orbiter as Mercury's gravity tugs it this way and that, scientists can map the planet's gravitational field with extraordinary precision. Variations in that field correspond to variations in the density of material beneath the surface. Dense regions pull the spacecraft slightly faster. Less dense regions let it coast slightly slower. Over months of orbiting, these subtle accelerations and decelerations build into a three-dimensional picture of how mass is distributed inside the planet. Combined with topographic data from the laser altimeter, this gravitational map will constrain the thickness of the crust, the density of the mantle, the radius of the liquid outer core, and the size of the solid inner core, if one exists. That last point matters enormously. Whether Mercury has a solid inner core, and how large it is, directly affects the behavior of the magnetic dynamo. On Earth, the growth of the solid inner core is one of the primary engines driving convection in the liquid outer core. As iron crystallizes onto the inner core's surface, it releases lighter elements and latent heat into the surrounding liquid, creating buoyancy-driven currents that sustain the dynamo. If Mercury has a similar process occurring, it would help explain how such a small planet maintains an active magnetic field after 4.5 billion years. If Mercury's core is fully liquid with no solid inner component, it would require a completely different dynamo mechanism, one that operates without the energy source that drives Earth's field. Either outcome rewrites the physics of planetary dynamos. The composition of Mercury's core matters just as much as its structure. Messenger provided strong indirect evidence that the core contains lighter elements mixed with the iron, elements like sulfur, silicon, or carbon that lower the melting point of the iron alloy and could keep the outer core liquid at temperatures where pure iron would have solidified long ago. Bepi-Colombo cannot sample the core directly, of course. No instrument can reach 2,000 kilometers beneath the surface. But the gravitational field data, combined with precise measurements of Mercury's libration, the tiny wobble in its rotation caused by the tidal pull of the Sun, will constrain the core's density with a precision that allows scientists to distinguish between different compositional models. A core rich in sulfur has a different density than a core rich in silicon. The wobble amplitude depends on how much of the interior is liquid. By combining these measurements, Bepi-Colombo will narrow the list of possible core compositions in ways that directly test the formation theories we have already explored. If the core contains abundant sulfur, it supports the idea that Mercury formed from oxygen-poor, sulfur-rich building materials in the inner disk. If the sulfur content is low, it favors scenarios where Mercury's iron enrichment came from a different mechanism entirely. And here is where Mercury's story expands beyond its own orbit and begins to reshape how we understand rocky planets across the Mercury's galaxy. Over the past 2 decades, the discovery of exoplanets has transformed astronomy. Thousands of worlds have been catalogued orbiting other stars. Among them are the exomercuries we encountered earlier, dense, iron-rich worlds orbiting close to their host stars. But in that discussion, we used them to argue that Mercury's formation was not a fluke. Here the question shifts. If these worlds are common, and if we want to understand what they are made of and how they came to be, we need a calibration point. We need a dense, iron-rich planet that we can actually study up close. We need Mercury. Understanding these worlds from afar is one of the great challenges of exoplanet science. We cannot send spacecraft to them. We cannot land on their surfaces or sample their rocks. We can measure their masses from the gravitational wobble they induce in their host stars, and we can measure their radii from the dips in starlight when they pass in front of those stars. From mass and radius, we calculate density, and from density, we infer composition, crudely, with large error bars and many assumptions. Every one of those assumptions is built on our understanding of how rocky planets form and what determines their internal structure. And that understanding is anchored, whether scientists always acknowledge it or not, in the study of the 4 rocky planets we can actually examine up close. Mercury, Venus, Earth, and Mars are the calibration points for all of exoplanet science. They are the only rocky worlds whose compositions, structures, and histories we can study in detail. Every model that predicts what a rocky exoplanet should look like is, at some level, tested against these 4 objects. Mercury is the extreme endpoint of that calibration set. It is the densest, the most iron-rich, the most compositionally unusual of the 4. If our models cannot explain Mercury, they cannot reliably predict the properties of dense, iron-rich exoplanets either. Every theory about Mercury's formation, the magnetic sorting of iron in protoplanetary disks, the hit-and-run collision scenario, the chemical gradient model, carries implications for how we interpret the interiors of worlds we will never visit. If the magnetic sorting model is correct, it means the magnetic properties of a host star during the planet-forming era influence the compositions of the rocky planets that result. We currently have no way to measure those magnetic properties for distant stars, which means a major variable in planetary composition has been invisible to exoplanet science. If the hit-and-run model is correct, it means the collision histories of young planetary systems leave permanent imprints on the structure of the surviving worlds. imprints that might be detectable as anomalous densities in transit surveys. If Mercury formed farther from the Sun and migrated inward, it means orbital architecture alone cannot tell us where a planet was born. Each of these possibilities changes the interpretation of exoplanet data in a different way. And the only way to determine which possibility is correct is to study Mercury itself in enough detail to discriminate between them. Bepi Colombo is not just a mission to the innermost planet. It is a calibration mission for the study of rocky worlds everywhere. There is another dimension to Mercury's broader importance that receives less attention but may be equally significant. Mercury's magnetic field, though weak, is real. It exists. It deflects the solar wind. It creates a magnetosphere, small and dynamic but functional, that partially shields the surface from the stream of charged particles pouring off the Sun. The fact that a planet this small can sustain a magnetic dynamo after 4.5 billion years is not just a curiosity. It is a data point with direct implications for the question of habitability around other stars. The most common type of star in the galaxy is the red dwarf. Red dwarfs are smaller, cooler, and dimmer than our Sun. Their habitable zones, the regions where liquid water could exist on a planet's surface, are much closer to the star than Earth's habitable zone is to the Sun. A planet in the habitable zone of a red dwarf orbits at a distance comparable to Mercury's orbit around our Sun, or even closer. At that range, the stellar wind is intense. Red dwarfs are also prone to violent flares that can strip atmospheres from close-orbiting planets over time. The question of whether such a planet can retain an atmosphere, and therefore whether it can support liquid water and potentially life, depends critically on whether it has a magnetic field strong enough to deflect the stellar wind. If the planet has no magnetosphere, the charged particles slam directly into the upper atmosphere, sputtering away atoms and gradually eroding the atmospheric blanket until nothing remains. Mars is the cautionary example. It lost its global magnetic field billions of years ago, and the solar wind has been stripping its atmosphere ever since. Today, Mars retains only a thin wisp of carbon dioxide, less than 1% of Earth's atmospheric pressure, too little to support liquid water on the surface. What was once a world with rivers and lakes became a frozen desert, and the loss of the magnetic field was a central factor in that transformation. Mercury demonstrates that a small, close-in planet can sustain a dynamo. That fact alone matters for the habitability question. But the details matter even more. How does Mercury's magnetosphere interact with the solar wind at such close range? How efficient is it at deflecting charged particles? Where does the shielding fail? And what are the consequences for the surface below? MESSENGER revealed that Mercury's magnetosphere is extraordinarily dynamic, with magnetic reconnection events, the process by which solar wind magnetic field lines link up with planetary field lines and allow particles to pour in, occurring roughly 100 times faster than at Earth. The magnetosphere is constantly being compressed, deformed, and reshaped by the solar wind. It is a shield, but a battered one, and understanding how much protection it actually provides is essential for assessing the magnetic prospects of similar worlds elsewhere. The dual orbiter measurements will also produce the most detailed portrait of a prospective Ballon Major, close-in planetary magnetosphere ever assembled, data that carries implications far beyond Mercury's own story. It speaks directly to one of the most consequential open questions in astrobiology: whether the most common type of potentially habitable planet in the galaxy can protect itself from its own star, or whether proximity to a red dwarf is an automatic death sentence for atmospheric retention. If Mercury's magnetosphere provides meaningful shielding despite its weakness, it offers hope that rocky exoplanets with similar fields could retain their atmospheres. If the shielding is too compromised by the proximity of the star, It suggests that magnetic protection alone may not be sufficient, and that habitability around red dwarfs may require additional factors we have not yet identified. This is the scope of what Mercury offers. Not just a puzzle about one small world, but a key to understanding the entire inner architecture of planetary systems. The planet that seemed least important turns out to occupy a position of outsized scientific leverage, the extreme case that stress tests every model, the boundary condition that every theory of rocky planet formation must satisfy. The habitability question connects to an even broader revision. If Mercury can sustain internal activity for 4.5 billion years despite its size, the timescales we assign to geological death on small rocky worlds everywhere may need to be extended. The window during which a small planet can maintain a magnetic shield, cycle volatiles through its crust, and support active surface chemistry could be significantly longer than current thermal models predict. That has implications not just for the dead worlds in our own system, but for the billions of small rocky planets scattered across the galaxy that we have written off as too small to matter. Mercury is proof that small does not mean finished. And yet Mercury remains, in the public imagination, the planet nobody thinks about. It has no rover sending back photographs. It has no dramatic clouds or rings to catch the eye in a textbook. It does not feature in proposals for human exploration or in science fiction stories about colonizing other worlds. It sits in the glare of the sun, too close to see easily, too hot to visit comfortably, too small to seem important. The very qualities that make Mercury difficult to study are the ones that make people dismiss it. That dismissal is itself a kind of lesson. There is a pattern in the history of science where the objects that appear simplest at the first turn out to be the most revealing when examined carefully. The hydrogen atom looked simple until quantum mechanics cracked it open and found a universe of complexity inside. The structure of DNA looked like a straightforward chemistry problem until its implications for heredity, evolution, and medicine remade entire fields of human knowledge. The cosmic microwave background looked like static until it became the most precise map of the early universe ever made. In each case, the simplicity was an illusion created by distance. The closer you looked, the more there was to see, and the act of looking closely did not just reveal the object. It revealed the limitations of the framework that had labeled the object simple in the first place. Mercury fits this pattern precisely. It is the smallest rocky planet. It is the closest to the sun. It has no atmosphere, no moons, no rings, no obvious drama. By every superficial measure, it is the least interesting member of the inner solar system. And yet, it holds the most extreme core-to-mantle ratio, the most unusual surface chemistry, the most unexpected magnetic field, the most mysterious geological features, and the most contentious formation history of any rocky planet we know. It is the object that looks the simplest and turns out to be the strangest. The assumption that small means simple is one of the deepest intuitive errors humans carry. We apply it to atoms. We apply it to organisms. We apply it to planets. We apply it to the quiet person at the back of the room who turns out to know more than everyone at the front. Simplicity is not a property of objects. It is a property of our attention. Things look simple when we have not looked at them carefully enough. And Mercury punishes that assumption every single time someone points an instrument at it and reads the data that comes back. The planet is small, yes. It is close, yes. And it is anything but simple. Consider what Mercury has forced scientists to reconsider in just the past 15 years. The idea that volatile elements cannot survive on planets close to their stars has been overturned. The idea that a small planet must be geologically dead has been overturned. The idea that an oversized core requires a catastrophic impact has been severely challenged. The idea that the inner solar system's composition can be understood without accounting for the Sun's magnetic field, has been challenged. The idea that a planet's current orbit tells you where it formed has been questioned. Mercury has not just added to our knowledge, it has subtracted from our certainty. It has shown us that some of the things we thought we knew about rocky planets were wrong, or at least incomplete. And incomplete knowledge, when you are trying to interpret the compositions and structures of worlds orbiting stars dozens of light years away, carries real consequences. There is something else that Mercury reveals when you step back and look at the 4 rocky planets as a group. They are not variations on a theme. They are 4 radically different outcomes of the same process. Earth has plate tectonics, liquid water, a strong magnetic field, and life. Venus has a crushing atmosphere, a runaway greenhouse, and no detectable magnetic field. Mars is a cold desert with a thin atmosphere and a dead core. Mercury is an iron ball with a thin rock shell, a lopsided magnetic field, and volatile chemistry that defies its location. These 4 worlds formed from the same protoplanetary disk, orbiting the same star, separated by relatively modest distances, and yet they could not be more different from one another. Understanding why these 4 planets diverge so dramatically from similar starting materials is one of the most important open questions in planetary science. And Mercury, as the most extreme member of the group, places the tightest constraints on any model that attempts to answer it. You cannot claim to understand rocky planet formation if your model fails on Mercury. It is the final exam. The history of Mercury exploration is a story told in 3 acts, and we are entering the 3rd. The first act was Mariner 10 in the 1970s, the first glimpse, the discovery that Mercury had a magnetic field and a surface that hinted at geological complexity beneath the craters. That act raised the questions but lacked the instruments to answer them. It was the equivalent of hearing a strange sound in the dark and not being able to turn on the light. The second act was Messenger, the first sustained study, the mission that mapped the entire surface, measured the chemistry, confirmed the ice, discovered the hollows, and catalogued the contradictions. Messenger turned on the light and found that the room was far more crowded and far more disorganized than anyone had imagined. The answers it provided were outnumbered by the new questions it generated. That act sharpened the questions into contradictions that no existing theory could resolve. The third act is Bepi Colombo, the mission designed from the ground up to resolve those contradictions, carrying instruments that were specified and built to test the specific theories that Messenger's data inspired. 2 orbiters instead of 1, global coverage instead of hemispheric, mineral mapping capabilities that Messenger never carried. A dual vantage point study of the magnetosphere that will separate the internal signal from the external noise for the first time. If the third act follows the pattern of the first 2, it will not deliver clean answers. It will deliver better questions. That is not a failure of science. That is how science works when it is pointed at something genuinely strange. Each generation of instruments peels back a layer and finds the layer beneath is more intricate than expected. Mercury has been doing this to scientists for 50 years. There is no reason to expect it will stop now. But even without the answers that Bepi Colombo will eventually provide, the current state of Mercury science is itself a revelation. The mere fact that 4 competing theories exist for the formation of a single planet in our own solar system tells us something important. It tells us that rocky planet formation is not a solved problem. It tells us that the processes that built Earth, Venus, and Mars are less well understood than textbooks suggest. If we cannot explain the simplest-looking member of the family, we cannot claim to fully understand the family. That humility is Mercury's most underappreciated contribution to science. Not a specific discovery, not a single measurement, but the reminder that the universe is under no obligation to be as simple as we find it convenient to assume. The next time someone asks you to name the strangest planet in the solar system, consider the smallest one. Consider the one sitting closest to the sun, the one everyone skips past, the one that does not make the highlight reels or inspire the mission posters. Consider the planet whose iron core fills 85% of its radius in a body smaller than 2 moons. The planet with a magnetic field that should not exist, offset in a direction no one predicted. The planet with volatile elements that should have been burned away billions of years ago, and ice hiding in eternal shadows just kilometers from terrain hot enough to melt lead. The planet with hollows that are carving themselves into the surface right now through a process that exists nowhere else in the solar system. The planet that is still shrinking, still cracking, still geologically alive inside a body that every thermal model says should have gone cold and silent long ago. Consider the planet that 4 separate theories are still fighting to explain. The planet that one spacecraft revealed to be stranger than expected and another spacecraft is about to study in detail for the first time. The planet whose existence challenges our understanding of how rocky worlds form, how magnetic fields persist, how volatiles survive, and how the architecture of an entire planetary system was assembled from a disk of gas and dust 4.5 billion years ago. Mercury is not the planet people think it is. It never was. The simplified picture, the hot, dead rock closest to the sun, was never an observation. It was an assumption, and every instrument that has ever been pointed at Mercury has returned the same verdict. The assumption was wrong. The planet is not simple. The planet is not dead. The planet is not understood. It is the world hiding in plain sight. The planetary outlier sitting at the front of the solar system where everyone can see it and almost no one bothers to look. It is the smallest planet with the biggest mystery. A dense metallic heart wrapped in a thin skin of contradictions, orbiting the sun in a rhythm no other planet shares. Holding ice in the shadows and losing atoms to the light, shrinking and cracking and generating a magnetic field that the physics says it should have lost billions of years ago. And the answer to that mystery, when it finally comes, will not just explain Mercury. It will reshape how we think about every rocky world orbiting every star in every corner of the galaxy. It will change the models we use to predict what exoplanets are made of. It will refine the criteria we use to assess which worlds might be habitable. It will deepen our understanding of the disk of gas and dust from which our own planet formed. Mercury's strangeness is not a curiosity confined to one small world. It is a thread that, when pulled, unravels assumptions that run through the entire framework of planetary science. The instruments are on their way. The orbit insertion is months away. The data is coming. 2 orbiters, 16 instruments, and a planet that has been defying expectations since the first telescope was aimed in its direction. Mercury has been waiting 4.5 billion years for someone to understand it. 2 spacecraft have tried. One flew past 3 times in the 1970s and never came back. The other circled for 4 years and then was pulled into the surface, becoming part of the world it studied. The third is arriving now. What it finds will not settle every question. Mercury does not work that way. But it will bring us closer to the truth than we have ever been. And the truth about Mercury, whatever it turns out to be, will be stranger than the story we have been telling ourselves. It always has been. The smallest planet is still teaching us the biggest lesson. Pay attention to the things you think you already understand. They are almost certainly more complicated than you believe. Mercury is proof